The occurrence of cosmic rays, especially the ones we're studying at the highest energies, represent some of the most energetic phenomenon in the universe. In particular, the cosmic rays we're studying are single particles, possibly protons, with energy 10 million times higher than that which is being produced at the Large Hadron Collider. That it has a 6 kilometer diameter ring in Switzerland, and so that's an enormous object on Earth just produced 10 to the 13th electron volts, and that's the unit of energy we use. Whereas the ones we're looking at go up to 10 to the 20th electron volts, so a factor of 10 million more.
Cosmic rays are the particle, very energetic particle from outer space, and they propagate through the universe and then finally impinge on our Earth's atmosphere.
An electron volt is exactly what it says it is. It's you take an electron and you put it in an electric field. An electric field creates a force on that electron because it has a charge. And if you take that electron and you move it through a potential of 1 volt in an electric field, the amount of work or the amount of energy it took to do that is one electron volt.
Back in 1991, the Fly's Eye experiment, so sort of the first generation cosmic ray experiment that we were doing here, saw one event at 3.2 times 10 to the 20th electron volts, which is still the highest energy particle ever observed by man, or the same amount of energy as in a fast pitch baseball. Those things are, trillions of atoms. We're talking about 1 proton with the same amount of energy.
Hi, my name is Charlie Ray. I am a professor of physics and astronomy here at University of Utah. I am also the principal investigator for the telescope array experiment, the Utah group. At the same time, I'm also one of the co-spokespersons for the experiment as a whole, which has collaborators from Japan, Korea, and Europe, as well as the United States. We use, as an experiment, 2 different techniques to detect cosmic rays. These techniques are complementary in the sense that they measure and give us information about the original cosmic rays that the other does not. One of these techniques is called the ground array technique, and where we use an array of very widely dispersed particle detectors on the ground. In our case, they're separated by 1.2 kilometers to 2 kilometers, depending on which part of the array we're looking at.
We have 3 air fluorescence observatories. These are telescope observatories. They're not telescopes in the standard sense that people think of telescopes. They have a big mirror and they focus light onto very sensitive photomultiplier detectors that can measure very small amounts of light in very short amounts of time. So we have big mirrors in order to capture enough light that we can focus on the light onto these very sensitive detectors and basically make a movie of that shower as it passes through the atmosphere. We're not looking out into space like something like the James Webb telescope or the Hubble telescope or ground-based telescopes. Our telescopes are looking into the sky, into the Earth's atmosphere. And each station is positioned just outside of the array and looking out over the array. This is a very large array so that we can see these showers as they pass through the atmosphere above the array and then measure the particles when they hit the ground and are detected by the particle detectors on the ground. My name is Stan Thomas. I'm an engineer that works with the Cosmic Ray Research Group at the University of Utah. I've worked with this project for quite a number of years, from its origins as the Fly's Eye project at Dugway Proving Grounds all the way through until now. We now have sister experiments in the southern hemisphere. So this research has come a long way. It's very difficult research that takes many years and big experiments to do, but we've made enormous progress.
So on the way down from Salt Lake, we stopped briefly. There's a really old Sinclair gas station. It was built in like 1917. The town of Eureka, which I think is an old silver mining town. We saw the jail and the city hall and Porter Rockwell's old cabin. Porter Rockwell is a guy who met Joseph Smith and became one of his early followers. We saw the Intermountain Power Plant, which generates power for the city of Los Angeles. There's a volcanic source of beryllium out past the Middle Drum Telescope site. That's one of the largest sources of beryllium. I think it's the largest in the US and one of the largest in the world. My name is John Matthews. I'm a research professor at the University of Utah. We've driven down the west side of Utah Lake, and now we're here at the Cosmic Ray Center in Delta, Utah. This front room is a room for introducing the public to our experiment. It's sort of on the way to the Great Basin National Park. A bunch of people stop here and see what it is that we're doing and find out about the detectors that they see out in the desert here.
Scintillator detector is a type of detector that relies on organic molecules or something within either a liquid or a plastic that will get excited by the passage of a charged particle and emit light. The scintillators that we use are typically sheets of transparent plastic with some chemicals in the plastic that scintillate, that produce light when charged particles go through the plastic. So we'll seal those sheets of plastic inside light-tight covers, so it's absolutely light-tight inside, and then any light that's produced by inside the plastic will bounce around inside the plastic, and through fiber optics and other things in there, we channel that light to detectors which convert the light to electrical signal and allows us to measure the passage of charged particles from these showers that are produced by the cosmic rays that pass through these sheets of scintillator plastic.
Going to the SDs themselves is often an adventure in and of itself because the roads out there are inconsistent and you only have some dirt trails and farm access roads. So oftentimes you can only get so close before you have to hike maybe a mile, 2 miles to go to the SD itself before you can even begin to work on it. Occasionally you have to go out there and clean a solar panel because if they get dirty, they're in the desert, things happen. Occasionally you have to go out and you have to restart the computer. Much like any other computer, it can have technology issues, and sometimes a simple system restart does it. Occasionally it's a much more complex issue. You have to grab the computer board from the SD itself, take it back to the house, away from the desert, into a much more controlled environment where you can edit the resistors, edit how the circuitry is working, stuff that takes a lot more precision than you can do in the desert. That means that you have to take 2 trips. You have to go out there, get the SD computer, and then bring it back to the desert.
So what we do is we use the atmosphere of the Earth itself as our detector. And when these very extremely high energy particles arrive at Earth from whatever their origin was, they'll eventually collide with the nucleus of some sort of molecule in the atmosphere, and they'll just absolutely obliterate that nucleus.
So then the first particle goes to another one and make another one and another. So this chain reaction makes like a shower profile. So by using our atmosphere as a detector, we can detect those cosmic ray showers, which is called extensive air shower.
The shower of particles will hit the surface of the Earth, and it's spread over a big area on the surface of the Earth where these particles hit. And we put scintillator detector stations at various positions on the ground, so we can measure exactly what time the shower particles hit each detector and how many particles hit each detector, which allows us to basically get a footprint of the shower as it hit the ground. Now, if the shower was coming straight down, all of the detectors, all the particles will hit all of the detectors at the same time. If the shower is coming in at a steep angle, then it will hit the detectors over here first, and then it will hit here and here and here, and it will hit the detectors on the other side last. So we can get an idea, a very precise idea actually, of what direction that shower was coming in, and then the pattern of particles on the ground that we can use to infer information about the original cosmic ray. But the detectors themselves are big, heavy things. They're 1,500 pounds or so. And so we can't just carry those out on our backs and put them in the field. And we don't want to drive them out with trucks and damage the land. So what we do is we use helicopters to deploy these and put them out in the field, and eventually to remove them from the field when we finish. And we'll carry these. We have 800 or so of these detector stations distributed all over Millard County and part of Juab County in Utah, and spaced anywhere from 1.2 kilometers to over 2 kilometers between them. And we'll carry each one out to a precise location and set it in place using a helicopter.
So with the ground array, we look at the lateral spread of particles. With the fluorescence detector, and it's called fluorescence because the light that is emitted is that which is generated by charged particles going through a thin gas, just like what you have in the fluorescence light. In any case, these showers give us pancakes of particles moving through the air, essentially at the speed of light, a few hundred miles an hour slower than the speed of light, and they last a few millionth of a second, and we can capture these with really, really fast cameras. It's not something you can see with your bare eyes. It does, however, give us the ability to look at how the shower develops. We can actually track more or less the number of particles as it comes down through the atmosphere. And that development actually gives us additional information from which we can extract what the original particle might have been, whether it's a proton, a helium nucleus, or something heavier.
The fluorescence telescopes works at night, and we are using the UV light, which was produced by cosmic ray, and by using mirrors, then we can get their information by reflected these mirrors and capture those photons using our photon multiplier tubes. Those UV light is quite faint, so we need a moonless and clear night.
I'm Jeremy Smith. I'm a senior electronics engineer with the telescope array. This is basically a light cone attached to a camera that we use for testing. I use it mostly for testing new software, make sure that any changes I make work. Debugging here is much easier than debugging at the site in Delta. This is a little UV LED flasher unit. This is a light cone, camera is behind it. Right to my left here is one of the electronics racks that we use to actually collect the data. I do the first couple of nights of every run period. Those are relatively short, which gives me time to do repairs and such. I try to arrive at the site about 3 hours before the dark period commences. Turn things on, find problems, fix them. About a half hour before, we turn on high voltage and do calibration runs. I spend, basically until either moonrise or astronomical twilight ends, basically just collecting data. Every hour or so, we have to go outside and look at the sky, record where clouds are. We usually have one person at the site, one person remotely running. We're in communication with them, currently using Zoom.
About 7 years ago, based on the first 5 years of telescope array results, we saw what appeared to be a hotspot, something that's of the size of the order of 20 degrees in radius in the sky, pointing towards the Big Dipper, Ursa Major, of excess. Above that energy, a quarter of the particles that we saw fell within that 20-degree radius circle, which only amounts to about 5% of the northern sky that we view.
So mostly by using their arrival direction, we can estimate some concentration of the cosmic ray or some deficit of cosmic rays we are observing. If we see some area of the sky and we can observe more events, more cosmic rays towards a certain area, then maybe we can conclude there towards that direction, something is there to produce more and more ultra-high cosmic rays. So I'm studying that one by using a statistical analysis method. So we compared it to the distribution of ultra-high cosmic ray on the sky compared to the isotropic simulation result. Then we can guess, towards this direction, we have more events, then maybe we need to focus on that direction to understand the possible sources are there or not.
And to actually get a better handle on this, we just need many, many more of these cosmic ray events. And so we are quadrupling the size of our detector to try and get 4 times as much statistical power over the same period of time. And the idea is that over the next 5 years, we should be able to triple the overall statistics of the experiment, which has been taking data now for over a decade.